Let's look at another application of the divergence theorem. Say we have this surface which includes the upper hemisphere and the plane z equals 0. So this actually represents the boundary of this solid region here, this gumdrop, so to speak. So we have the hemisphere here, and then of course the plane z equals 0. So this surface made up of these two pieces acts as the boundary for this solid region here. So this is something we've seen before. That is, x runs from negative a to a, y runs from the negative square root of a squared minus x squared to the positive square root of a squared minus x squared. And then of course z runs from 0 to the square root of a squared minus x squared minus y squared. So again, if we're interested in computing the flux of a vector field across this region, or surface as you say, then we have to do another surface type integral. But of course that would mean dividing the surface integral into two pieces, which is actually more work. So we think of the divergence theorem. So here is our vector field, xy, comma, yz, comma, negative yz. And of course, to utilize the divergence theorem, we need to take the divergence. So we do the x partial plus the y partial plus the z partial. So that gives us a y plus a z minus a y, which is just z. Now, again, the surface integral of the vector field across the surface S, in this particular case, is denoted by these symbols. And of course, the divergence theorem allows us to replace this surface integral with the triple integral of the divergence across Q. So now what we do is simply replace the divergence here with what we computed it to be, z. And then again, you look at this region here and say, well, that has lots of circular symmetry, so we can use cylindrical coordinates. Z is z, but we can replace the xy Cartesian coordinates with the standard polar coordinates. So we're going to go ahead and move to those, since there's no reason to keep writing something that's going to sink. So we have 0 to 2 pi for theta, and 0 to a, of course, for r. And of course, the new area element, or new volume element in this case, will be r dz dr d theta. And of course, we're left with the z from the divergence. And now, of course, the coordinate z has an upper bound of a squared minus r squared. We just simply replace x squared plus y squared with the r squared and then put in the negative. So we're all set with the cylindrical coordinates. So now with the z here, we add 1 divided by the new power. And of course, there's no theta dependence in here, so we can go ahead and break up the theta integral and move it over to the left, as we've done many times. So that's a multiplicative functionality that we're going to take advantage of. So now, of course, we have the 1/2 z squared, and we evaluate lower limit 0 and upper limit square root of a squared minus r squared. And of course, the lower limit just zeroes out the antiderivative. And so when we substitute, we can go ahead and pull the 1/2 to the side, and we have a squared minus r squared as the z squared absorbs the radical. And now, if you will, go ahead and absorb the 2's here. We get a pi, and then of course we multiply by r, and we get what? A squared r minus r cubed. And of course the integral with the theta I didn't say much about. That's just 2 pi. That's so simple we forget about it. And that's of course the 2's absorbed, as I said before. And so now we add 1 divided by the new power, so we get pi. So we have a squared r squared divided by 2, and then of course we have the negative r to the 4th divided by 4, evaluated from 0 to a. So what we're seeing, again, as we've seen many times, the cylindrical coordinates, the spherical coordinates, polar coordinates really do make our computation simpler. And so, of course, now the lower limit will give us 0, but we can evaluate it a, and that'll give us a to the 4th divided by 2 minus a to the 4th divided by 4. We get a common denominator of 4, and we have 2 copies of a to the 4th minus 1 copy of a to the 4th, and that gives us pi times a to the 4th divided by 4. So again, we see that there's a lot of time that's saved in applying these vector calculus theorems. It doesn't mean that the problem is super simple, but it's certainly less busy and usually cuts down on the tedium. And we are done.